All right, so here's a short one for you. Just a few examples. We're going to be working on building quadratics today, right? So now that we know all of the properties of quadratics and how they're nice and the vertex and the symmetry and all of that, now we're going to use that to fit it to situations, like where would this actually apply and how can we use this? So that means obviously word problems, and those are kind of fun because the translation from words to math and numbers is a really important skill, and it can lead to some really funny kind of problems. So my advice is that in lots of the problems in this section, what we're going to be focusing on now might need two equations to solve a word problem. The first equation would be what I call the parameter equation, not perimeter, right? Not the outside of a shape. Sometimes that's true, not always. The parameter equation is also a limiter equation. This is what's going to be like, we only have this many feet of fence, or we only have this far that we can go, or whatever. The other equation is going to be the quadratic, and this is going to be what we want to optimize. And by optimize, we mean maximize or minimize. Since it's a quadratic, it either opens up or opens down. And so that's what we're going to be working on, is we'll end up having like two different unknowns in the problem, and we'll solve one equation for one of the variables and substitute that in, and all of a sudden we have a quadratic that we can now optimize. The most important thing you can do, though, is to draw a picture with labels, right? Knowing what we're talking about is super important. So that's my most important piece of advice. But also be paying attention to, maybe I need two equations. Maybe I know this piece of information and I'm trying to optimize this piece, and they're not really related, but they do have some interconnecting pieces. That's what we're going to see the most. A couple other things. Revenue is the product of the number of units sold and the price. So that's something that they're kind of assuming that you know at this point. So revenue is the cost times the price. And so it's written R equals XP. X would be the number of units sold and P would be the price. And it's often a quadratic because the price will be a function of how many units are sold, or the number of units sold will be a function of price. Very, very often, the number of units sold is a function of price. And so that will make it a quadratic. They're usually negatively related. As price increases, the number sold decreases, right? So we generally get a quadratic that opens down, and we want to maximize it. Okay. So my first example is saying I have a garden. Suppose I want to fence it in. I have 100 feet of fencing, and my garden is right next to my house. So I only need to fence 3 sides of my rectangular garden. I didn't put that in here, but it is going to be rectangular. What is the maximum area I can enclose, and what dimensions create that maximum area? Now, I could potentially do a circle, but I don't want to deal with pi yet, and I'm probably thinking you don't either. So we're going to go rectangular. I should have included that in here. But okay, so let's say that my house is here and my garden is here. I'm going to make the size of my garden right. I need 2 letters. You can pick your 2 favorite letters. I usually use X and Y. Some people like to use L and W, A and B. Pick your 2. Sometimes I'll use M. Maybe I should use M and W just because those are my initials. Pick 2 letters. Okay, so now everything I know. I have 100 feet of fencing. I only need to do the 3 sides. I have 2 X's and 1 Y. So I only have those 3 sides to cover. And I want to maximize area. Okay. So this is one of those situations where you need 2 equations. My perimeter equation is going to be 2x plus y equals 100. That's my perimeter and parameter equation. This is my limiter, right? I only have 100 feet of fencing, so I need to figure how that works. But then the area, the thing I want to optimize, is xy, right? That would be the area of that rectangle. So now I have my two equations. This is helpful. But I can't optimize this xy, until they're both the same variable. But I can make that happen. If I solve this and say, okay, I want to get, say, y alone, because I don't have to divide anything by 2. Y equals 100 minus 2x, yeah? So now I sub that in here. So the area equation becomes x times 100 minus 2x. Now this is a function I can optimize. This is negative 2x squared plus 100x. So the vertex is at negative b over 2a. So x should be 25. And then y would equal 100 minus 2 times 25. So that's 50. So the dimensions would be 25 by 50. So that's the dimensions. The max area is going to be 25 times 50. 1,250 square feet. So there we go. We used a parameter equation, right? My limiter was how many feet of fence I had and what dimensions I needed to do to add up to that. And then my area is what I wanted to maximize. A lot of times I'll start there. What equation do I want to maximize? And then what else do I know that doesn't fit in here? That helps a lot. I drew my picture. I had labels on it, so I know what x and what y are, so I know that your dimensions are making sense. And they're following all the right rules. And then I did out the math. I found the vertex, right? That's all we need is the vertex. I could have, in case you were wondering, also taken 25 here and put it into my area equation and said negative 2 times 25 squared plus 100 times 25. And that would have also gotten me the 1250. So that's what a lot of the word problems here are going to look like. Let's do another one. Now we have a suspension bridge. The weight is uniformly distributed along the length, and it has identical towers that extend 75 meters above the road surface and are 400 meters apart. I need to draw this. 75 meters up, 400 meters apart. The suspension cables are parabolic in shape and suspended from the tops of the towers and touching the road's surface. There we go, at the center of the bridge. Find the height of the cables at a point 100 meters from center. Okay, so this is a word problem where we're not actually asked to maximize or minimize anything. We're asked to model the quadratic, like I think we talked about last video, and then use it to predict a value or to know a value. So let's set this up where we're on a coordinate plane. Here's the center of the road, and we're going up to each side. This is going to be 200. It's going to be negative 200 because that's the half width. This is going to be 75. And now I have the vertex and another point. The vertex is 0, 0, and the other point is 200 on the 75. Okay, so using my formula, I have y equals a x minus h squared plus k. All right, then I'm going to sub in for x and y. So this is going to become 75 equals a times 200 minus 0 squared plus 0. So I'm just going to leave that off. So a is going to equal 75 over 40,000. That's a very small a. 75 over 40,000 is 0.001875. I like the fraction better. Okay, so now we want to know at a point 100 meters from center. Well, the way we set this up, with the vertex in the middle at 0, 0, we just need to put in 100 for x. So y equals 75 over 40,000, 3 over 1,600 if you're doing it reducing, times 100 squared. I get 18.75. So that's how many meters high the cables are 100 meters away from the center. So this was a case of just needing to model it and then use the information that we had to find, okay, what's 100 feet from center? We just put in 100 and sub it in for x. So you'll definitely see some where you have to optimize, whether it's with the revenue equation or another area equation like this, or maybe we're trying to maximize some window or something like that. And then the suspension bridge, where we're modeling a quadratic and using that to fit. The other kind of problem that we might see is one where we need to use quadratic. We know what linreg is, right? We did the best fit line for a linear function. Now we're going to do best fit line for quadratic. It's in the same place, stat, calc, and then quadratic, right? So wherever you found linreg before, it should be right. It should be right underneath it. So this problem, we're going to let the individual's income vary with your age. So this table shows the median income for males of different age groups within the U.S. from 2012. For each age group, we're going to let the class midpoint represent the X, and for the class 65 years and older, we're going to just let their midpoint be 69.5, so it's simple. So our first thing is to draw a scatter plot with the calculator. So I grab my calculator, go to stat, go to edit. This is on the TI-84, and just start typing in the 19.5, 29.5, etc. That's your list 1. 10,869, 34th, 113, that's your list 2, etc. So we fill all that in, and then we're going to scatter plot and tell it to make the scatter plot. Okay, do that, and then I'm going to show you what I got. Okay, here's my graph. Median income looks like a negative parabola. Okay, now we need to find the quadratic function of best fit to this with our calculator. I did that. Stat, calc, quadratic. If everything's in there, you're fine. And then it's going to give you A, B, and C. So we're going to fit A, B, and C into this equation. I got negative 44.7586 for A, 4,295.3557 for B, and negative 55,045.4182 for C. So I slipped those all in. So that's my quadratic function of best fit to this. I didn't graph it on my graph here because Excel is not that nice, but you could graph it if you just type that into your y equals and see it all together and see how well it connects those points. But now we're asked to use that model. Okay, so we've got it. Now what does it do? Well, it lets us predict stuff. So based on this model, at what age can you expect to earn the most money? Maximizing any quadratic means finding the vertex. So we're going to find the vertex. Negative b over 2a gives me 47.9836 years old, which Looks about right. The highest point on here is the 49.5. And it looks like it's actually kind of starting to come down there already, so that 47, 48 years old makes sense, according to this. What is that peak income, though? Well, we'll just sub it into the function, and I get $48,000, which also makes sense based on the Y scale of my graph. So something must have gone pretty right for me to have this work. So remember when you're doing problems like this that you definitely want to draw a picture. I drew a picture for the 2 word problems we did that didn't require quadratic, and I made a picture with the one that required quadratic. So pictures are a huge part of this. They don't have to be pretty, they don't have to be perfect. They do need to be clear, like what am I measuring, what am I estimating, etc. Make sure you label things, right? I labeled all of my points when I was fitting my line. I labeled my X and my Y scale when I made my quadratic. I labeled my sides of my garden when I made that. So label everything and draw your pictures. And then use the stuff we already know about quadratics. We know the symmetry. If it's 100 feet, if we go over 100 feet and we go, or sorry, if we go over 100 meters and we go up 18.75 meters on one side, we're going to do the same thing on the other side because it's symmetric. Make sure you're using that and the intercepts and symmetry to help you with these problems. And then also remember that the calculator or whatever calculator function that you're using, Desmos or GeoGebra or whatever you're using, make sure that you remember it is a good resource and that obviously you can't do quadratic in your head, but that's what technology is for. So be comfortable with whatever you'd be using on a test and get some practice with this. Word problems are a huge part of life. So I really like word problems. And so kind of get used to seeing them and working with them and trying to translate, because that translation is the most important piece. And it also tends to be the hardest. So that's what we'll practice with the most.